Here's the bell work. What is the y-intercept for the graph? It doesn't show the graph, but we got the two equations right there. So to find the y-intercept, we're going to change these into slope-intercept form. So first thing we're going to do, two steps. We can do it in two steps, right? Change these to slope-intercept form. So that'll give us the y-intercept. So subtract 10x from both sides. Like this, right? It's going to zero out those 10x's. Then we can drop the negative 30y. And this equals, yeah, the 150 and negative 10x, they're not like terms that we can combine, so we got to keep them separated as separate terms. Negative 10x and positive 150. And then divide all the terms here by negative 30, the coefficient of y, which makes it a phantom 1y, and that's what we wanted because this changes it immediately into slope-intercept form. So the coefficient of x now, negative 10 divided by negative 30 is 1/3. And plus 150 divided by negative 30, that's going to be negative 5 right there. So that means the y-intercept, which is all we want on this one, is 0, negative 5. Of course, we know the slope now as well, 1/3, and that's okay. Same thing on number 2. So it's a negative 4x to zero it out. We're going to have to add 4x, but if you do it to one side, you got to do it the other side, okay? So negative 4x plus 4x is 0. So that zeroes out just like we wanted. We'll drop the negative 7y, which equals, we got 4x and positive 28. Then we'll divide all the terms by the coefficient of y, negative 7. But again, by all the terms to make that a phantom 1. Y equals 4 divided by negative 7. We'll just write that as negative 4/7 x. And then 28 divided by negative 7 is negative 4. So that tells us the y-intercept is 0, negative 4. Which is all we need. Here's our objective. I can determine when a relation is a function. Just take 30 seconds and write that down, please. A couple things about functions that you're going to want to know, all right? Is a function is just a different way to write an equation, but it comes with, I guess, one condition, okay? So before, let's compare with slope-intercept form, which we should be pretty familiar with now. Y equals mx plus b, okay? So this is slope-intercept form of the equation of a straight line. Now, equations or lines that are written in this form of this equation, they are also functions. So as a function, though, the only thing that changes is instead of writing it as y, we write it like this. All right, so now it would be that equals mx plus b. Now m is still slope, and b is still the y-intercept, all right? But the y now is written a little different, and this reads the f is function based on the x, okay? So in science you learn that x is independent and y is dependent, which mathematically means that we can write it as a function that depends on x. Now we don't usually say always f or function of x. We just say it as f of x, knowing that f stands for function. So we'd say function of x equals the slope times x plus the y-intercept. And that would be the general form for a straight line equation. All right? So again, this is f of x. So in fact, I'll write that down. F of x. That's how that would read, mathematically speaking. Okay? So determining when a relation is a function. Okay, there's only really two questions you have to ask yourself. And this is really just for tables or lists of points. We'll talk about how to tell on graphs here in a moment. All right? But you're going to go through two questions. You're going to look for any x values that repeat. So are there any x values that repeat? All right, so that's our first question here. Are there any x values that repeat? If the answer is no, then it's a function. All right, I'll give myself some more space here. If the answer were yes, there are x values that repeat, then we go to question 2 here, all right? So question 2 is, are there any different corresponding y values? All right, so then we'd check that. Then we run into another yes-no situation, right? So it's if the answer is no, they are not different, then it's a function again. If the answer is yes, then it is not a function. Like this, okay? Now that's in a table. Sometimes they'll give you a list of ordered pairs not in a table. And we're also going to see things that we call mappings in this, which is brand new for us. So we'll talk about those briefly. A mapping is just a different way to write out a table. Now something else we're going to need to be aware of in this lesson is the domain and range. Right? The domain and the range. This is going to be on the assignment. So the domain is just a list of x values. And then the range is just the list of y values. Now keep in mind, if you were to answer this type of question by hand, what's the domain and range? We usually put these lists in fancy brackets, all right, which look something like this. Try that second one again. There we go. Now if you needed to do fancy brackets by hand, to open it up, it's just an S and then a 2, like this. And then to close it up is just a 2 and then an S, like this, right? And then in between those fancy brackets, you'd have a list of all the x values for the domain and a list of all the y values for the range. So Jason is spending the week fishing at the Springfield Fish Hatchery. Each day he catches 3 fish for each hour he spends fishing. This relationship can be modeled by the equation y equals 3x, where x equals the number of hours spent fishing and y equals the number of fish caught. Yeah, I don't know who actually fishes at a fish hatchery. It seems kind of jacked up, but apparently you can catch only 3 fish per hour fishing there, okay? Now, if this is true, 3 fish for every hour he spends fishing, and in the table, one thing we should notice is the labels, right? It even says x, that's all the x values, that's the number of hours he spends fishing, and then the y value is the number of fish caught. They may not always put the x and y's there, but no, for a vertical table like this one, usually the x's are on the left column, and then the y's are in the right column. If it were horizontal, the x's are usually in the top row, and then the y's are usually in the bottom row, okay? But you may see some of those horizontal tables. But in this case, 3 hours and 3 fish per hour, right? So it's a 3 hours, and 1 hour would be 3 fish, another hour, another 3 fish, and then another hour, 3 fish. That's a total of 9 fish caught, okay? And yeah, it is possible to use the equation, of course. Y equals 3x. Y is the number of fish caught. X is the number of hours. So the second row with 2 hours spent fishing, let's say, okay, he spent 2 hours fishing. 3 times 2 is 6. So Y is 6, which means that it would have been 6 fish caught. And yeah, we can kind of repeat it with equation if we'd like. On the next time he goes, it's for 1 hour, so 3 times 1 would be 3 fish caught, okay? And it fits in this relationship that they gave us, y equals 3x, right? So 2 hours, again, another 6 fish caught. If he goes for 0 hours, naturally we would expect 0 fish caught. And then finally for 4 hours spent fishing, 4 times 3, boom, 12 fish caught on this one, all right? Now all of these are ordered pairs, which means we have x and y corresponding values, x and y corresponding values, right? So these are all ordered pairs that we can put in the graph. Now, there's going to be situations where you're not given a table, but you're given ordered pairs. If you need to put them in a table like this, that's fine, all right? Now, before I put this on a graph, let's just determine if this table is a function or not. So we'd look and would see, okay, is there, remember, two questions, right? Are there any x values that repeat? So I don't care about the y values, only the x values, right? And I say, oh, there is. There's a 2 here and a 2 there in the x values. Okay, so it's possible it could not be a function. Again, if there wasn't any x values that repeated, or that no x values repeated, then we could say it's a function automatic. But this one, it's showing two different x values. Two x values that are the same, different times. But the y values match, which means this one would be a function. All right, so that's in the table. We look for any x values that repeat. If they do repeat, then we got to look at the corresponding y values. If they're the same, then it's a function. If they were different, then it would not be a function. But again, going back to the first question, if all the x values were different, then it's automatically a function, okay? Now on this graph, we're going to have to label the x's. And again, in the table, it told us the x is the number of hours fishing. I'm just going to put number of hours. And then the y is the number of fish caught. All right, so I'm just going to put number of fish for the y-axis right here. Then we've got to put a scale on our axis. So we're going to start with 0. And I got enough space here I can say every other line is 1 hour. So there's 5 hours, 6, 7 hours. All right, 1, 2, 3, 4, 5. And then with the y-axis scale, I'm just going to say every line is a fish. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Did I count that right? No, I was off by 1. That's where 10 is. 12, 13, 14, 15. There we go. All right, then we just put these as ordered pairs on the graph. So the first time is 3 hours, 9 fish, right? So 3 hours, 9 fish would be this point right here. And then 2 hours and 6 fish, 2 and 6, boom, right here. And then 1 hour for 3 fish is this one. And then 2 and 6 again, it's just that same point right there. So I colored over it, but it's still the same point. Now we can know that that's 2 points. It doesn't really matter, okay? In fact, sometimes I'll just put a circle around it just to show that it's happened twice, okay? And then 0 hours, 0 fish, that's at the origin. And then 4 hours for 12 fish. So that would be 4 hours, 12 fish. See, make sure I'm on the right line. There we go. This point right here. Now, something else you'll need to consider is, do you need to connect the points? Well, if you did connect the points, then you'd end up with a point, for example, right here. This point right here represents half an hour, but also 1.5 fish, okay? Now, the problem with that is, well, you can fish for a half an hour. You cannot catch a fish and a half, right? And it could be cut in half. That's not really what I'm talking about. This can't happen, which means that we wouldn't actually put that point on there, okay? So I'm going to erase it. And that also means that you cannot connect the points. And remember, when we connect the points, it means that all the points on the line make the equation true. But you can't have half a fish, so it can't be true that way, all right? So this is the graph. Now, to tell if a graph is a function, it only takes what we call the vertical line test. So the vertical line test is where you take a vertical line, like this orange one here. See that orange line right there? Vertical, straight up and down. And then I'm just going to scan my graph, all right? So I start here. And what I'm looking for is any time on this vertical line where I get 2 points instead of 1, right? So I connect with the orange point there at the bottom, but it doesn't connect anywhere else. There's no other points on that line. Same with the green one. Same with the purple one. Now, the purple one happened twice right there, right? But it's at the same point, so it's not technically different. So I keep scanning the red, but there's no other points on that vertical line, and then the blue, all right? So from the vertical line test, on this one, we would also say that it is a function. Now you may ask, well, How do we know on a graph if it is not a function then? Let's look at an example. So you could look at a graph like this one, and you can only look in the first quadrant if you want, but we got all 4 quadrants on this one. So if I looked at a line like this, and then I'd say, okay, we got our vertical line, right? So I got my vertical line, and then I'm scanning this, and here to the left, I see it's only touching once right there at the bottom. See that? But as I scan, as I continue to scan, like let's go right here. You see now that it's touching the vertical line here, here, and here. So that's 3 different spots, right? Now, those 3 different spots that it's touching the vertical line means that it's not a function, okay? And we could see if we were to move that line back a little bit, right? That's like if I were to look at this line right here, it touches at first about right here. And so I'd say, oh, it touches twice there, right? On the vertical line, which means that it's not a function right there either. So as long as it touches the vertical line 2 or more times, then it is considered not a function. But if it only touches once every time, then it is a function. So the situation we just did is not the graph, but the fishing one was a function, which we saw. We say the number of fish caught is a function of the number of hours Jason spends fishing. It's true. Let's look at this example though. So Sean is spending the week fishing. However, he is fishing in the Bear River. Each day records how many hours he spends fishing and how many fish that he caught. The table of values below shows this relationship. All right. So just looking at this table, we should be able to make the determination on if this is a function or not, right? So it'd say, okay, is there any x values that repeat? And yes, there is. We've got these 3s right here, right? Well, for those values of 3 hours spent fishing, see how the y's are different here? Since the y's are different, we would say this is not a function, just from the table. All right? So the table shows it's not a function. Let's show that the graph is also not a function. And again, they gave us the labels for each axis. So the x is the number of hours fishing, and the y is the number of fish caught. Let's put a scale on these axes. I'll do it the same way. 1, 2, 3, 4, 5. Every other line is 1 hour. So every line is a half hour. And every line will be fish again. Like this. Well, they gave us all the ordered pairs we need. We'll start with this 1, 4 right here. So 1 hour of fishing, 4 fish caught. Boom, right here. 0 hours of fishing, 0 fish caught. Kind of what you'd expect there. 2 hours of fishing, 5 fish caught. 2, 5, boom. 3 hours of fishing, 1 fish caught. 3 and 1. That's kind of rough, but you know, it does happen. But the next time Sean goes, 3 hours of fishing, 8 fish caught. Okay, 3 and 8 would be about right up in here. And then 5 hours of fishing, 5 fish caught. Like this, all right? So this is a graph, and again, we can see that we wouldn't want to connect the points. Now, keep in mind that it doesn't have to do, being a function has nothing to do with whether it's a straight line. Okay, like you could say, oh, this one curves, so that's not a function. But that's not true. It doesn't matter if it curves or if it's a straight line when determining if it's a function. In order for it to be a function, on a graph specifically, it just needs to pass the vertical line test. So I create a vertical line here, something like this, and then I take it and scan it. So start here, only once. Oh, there it is, twice right there. See that? So here and here. Since it touches twice at the same time, it is not a function. So for this one, we haven't seen domain and range yet. I don't think it's really on the worksheet. So on this one, let's list the domain and range on this, okay? So remember, domain is the x values, and then the range is just a list of the y values, okay? So when doing this by hand, we would use fancy brackets to open it up like this, and we use fancy brackets to close it off. Now, one thing we need to remember with domain and range is even if a value repeats, we don't put repeating values in the domain and range more than once. Okay, so in the domain, I'd say I'm going to look at all my x values right here, right? So x values, I got 1, 0, 2, 3. I'm just going down. Now the 3 repeats right here, but I'm not going to list it a second time because it's already listed once. And then 5. Now you may say, well, that's not in ascending order. It doesn't have to be. Okay, it just needs to be a list of the values, the x values. So let's look at the y values. That would be the range here. So I got a list of the y values. I got a 4, 0, 5, 1, 8. And then again, the 5 happens on this last row right here, but I don't need to list it a second time. So that is the domain and range. All right, that situation is not a function, which we made that determination. The number of fish that Sean catches is not a function of the number of hours he spends fishing. Yeah, compare and contrast the relationship of Jason's week spent fishing and Sean's week spent fishing. Make a conjecture. We already did about the kind of relationship makes a function and what kind of disqualifies a relationship from being a function. So remember, you're just looking in a table, you're looking for the x values. If they repeat, then you got to look at their corresponding y values. If they're different, it's not a function. If they are the same, then it still is a function. And then for a graph, right, we're just looking for it to pass the vertical line test, which we will see on the assignment. All right, Vanessa is buying gumballs at Vincent's drugstore. The mapping below shows the relationship between number of pennies, or x, she puts into the machine, and the number of gumballs she gets out. Now this is a mapping, right? Again, this is the first time we're seeing a mapping. Now a mapping is just a different way to write a table. Okay, each arrow represents something happening, and they already said x is the number of pennies she puts in, and then the y is the number of gumballs she gets out. Okay, so for example, this first line, right? It's from 1 to 2. It maps going from 1 to 2, meaning that Vanessa put in 1 penny and got 2 gumballs out. Right there, okay? And then the next time she goes, she puts in 2 pennies. How many gumballs? 4. So 2 pennies, 4 gumballs. And then the next time she goes to Vincent's drugstore, 3 pennies, but 6 gumballs. And the last time she puts in 4 pennies, boom, she gets 8 gumballs out, okay? So each of those, by the way, is an ordered pair. And then we're going to put this on the graph. They've already labeled and scaled the graph for us. Very generous. So 1 penny, 2 gumballs, that would be this ordered pair. 2 pennies, 4 gumballs would be this ordered pair. 3 pennies, 6 gumballs, this ordered pair. And 4 pennies, 8 gumballs, right here, okay, in orange. Now again, would we connect these points? The answer is no, because you wouldn't want to get a half a gumball out. Maybe it means someone's already chewed on it. But you definitely can't put a half penny in either, okay? So any values that exist between these points are kind of non-existent, more because of the pennies, I guess, than the gumballs, but still, okay? So that's the graph. Well, is this a function? Now, again, we didn't need the graph with the table, or we shouldn't, and we shouldn't need the table with the graph. From the table, we should be able to say, okay, this is or is not a function, because right here we see there are no x values that repeat, right? So automatically we would say that this one is a function. And then on the graph, we'd say, okay, let's run the vertical line test here. So I'm scanning there once, touches once, boom. So this one also a function, okay? Now, if you're wondering on a mapping, you can make the table if that's more convenient for you, but in order for it to be a function, each of the x values part of the mapping, which is always the left, part of the map, it should only have 1 arrow coming out of the left. It doesn't matter if you have the arrows pointing to 2 y's at the same time. It's just that you can't have more than 1 arrow coming out of the x's. So if by chance this one had like 2 arrows coming out of 1 right here, then automatically it's not a function, okay? So you'll want to keep that in mind because you'll probably see some examples like that. Then this last part says, write an equation for this relationship. Okay, so the equation part of this, right? We know that the number of gumballs is y. So let's say y, the number of gumballs is based on the number of pennies you put in. And from the table, we can see that you get another 2 gumballs for an extra penny. Another 2 gumballs for an extra penny, right? And we've seen this before, it's slope right there, or rate of change. That's 2 gumballs for every 1 penny. And that would be the equation right there. Now that's the equation, but how do you write it in function notation? It's f of x, remember that? F of x equals 2x. And each of these values in the table represents f of x, right? So this would be like f of 1. What did it equal? Well, it was 2 gumballs. Or this next one, that would be f of 2 equals 4 gumballs, right there, okay? So if you see this on the assignment, which you will, it'll say something like, evaluate f of some number. It just means that you're replacing x with whatever number's in this parentheses right there. It's saying the function depends on the x value being this value. So like this one, you'd say, well, f of 1, right? Well, 2 times 1 is 2, and that's what we get up here. So it gives us the ordered pair, 1, 2, 1, 2, 2, 4, 2, 4, okay? So it gives us a little bit more information when it's written in function notation, but it is just a little different. Just replace the y, it's now f of x. But we can only put f of x as long as it's a function. So yeah, that was a function, and we know why because of the vertical line test and then looking at the x values in the table. So Kevin is across town at Marley's drugstore. The mapping below relates the number of pennies he puts into the machine and how many gumballs it gets out. So this one, it's got 4 different arrows, but again, just from the mapping, we see 2 arrows coming out of one of the x values, the 2. And so right away, just from the mapping, we should say it's not a function, but let's just confirm it in the table because we're kind of new to the mappings, all right? So the first arrow here shows 1 penny, 2 gumballs. The next arrow here shows 2 pennies, 3 gumballs. And this next arrow shows 2 pennies, 4 gumballs. And this last one is 3 pennies at 6 gumballs, okay? So again, without the graph, we should know this is not a function because we see the 2's repeat in the x's, but they are different y values, okay? So this one would know it's not a function right away. And again, in the mapping, it shows because the 2 arrows are coming out of one of the same x values. And it could be more than 2 arrows, by the way. Again, you're just looking for 2 or more arrows coming out of the mapping in the x values. So it's not a function from the table, but let's confirm it in the graph. So I got 1 penny, 2 gumballs, 2 pennies, 3 gumballs, but then 2 pennies, 4 gumballs, and 3 pennies, 6 gumballs. So that's all those ordered pairs. And again, in the vertical line test, we got this vertical line. We scan it. There's only once. That's okay. But oh, now it's touching it twice at the green and purple right here. So this one, still from the graph, not a function. That situation was not a function, and we already know why. Let's go to Cody at Ted's drugstore, okay? The graph below relates the number of pennies he puts into the machine on different occasions and how many gumballs he gets out. And we'll explain how this gumball machine works, first of all, okay? So let's go and explain this gumball machine here. It's a little bit smaller though. There we go. All right, so this gumball machine, when you put a penny in, how many gumballs can we get? So each of those blue dots means that at different times that Cody's gone to this gumball machine, he gets a different number of gumballs. So when you put a penny in, you could get 1 to 10 gumballs, okay? And we don't know how many gumballs he'll get. But that's how this gumball machine is working. Now, the fact that we don't know how many gumballs are going to come out should tell us that this machine is malfunctioning. Because even the people that put this gumball machine out would want to know, is it going to be 10 gumballs? Should be within a range. But if you can get the same number of gumballs each time, it makes things a little bit more predictable for us. But this one's malfunctioning, which is why this one would not be a function. So in this example, is the number of gumballs received a function of the amount of money put in? And the answer to that one is no. And again, we can run that vertical line test on this just to check why. Well, as I scan this, I see that it's touching that vertical line in more than one place. 10 places to be exact. Therefore, it is not a function. All right, compare and contrast the relationship of the gumball machines at the different drugstores. If needed, revise your conjecture about what kind of relationship makes a function, what disqualifies a relationship from being a function. Yeah, so again, in the table, we're just looking for the x values to repeat. If they don't, it's a function. If they do, then we go to the second question. And if the y values are different, then it is not a function. If they are not different, then it is a function. Okay. Or if it's a graph, we just run the vertical line test. So the cost for entry into a local amusement park is $45. Once inside, you can ride an unlimited number of rides. Okay. So they've already started the table for us, labeling the x and y's. And we know if you go on 0 rides, let's say you just go in the amusement park, no rides, boom, $45, right? But if you go on 1 ride, boom, $45. Okay? Because it doesn't matter how many rides you go on, it's still going to be $45 just to get in, right? So 2 rides, $45. 3 rides, $45. And yeah, you can take it extreme, like if you like to get sick on those amusement parks. You go on 100 rides, boom, still going to cost you $45 to get sick, okay? Now we're going to label the axes because we want to see what this graph looks like. And the x-axis here, that's going to be number of rides. And then the y-axis up here at the top. That's going to be dollars spent. So I'm just going to put a dollar sign there for cost. And we'll show the number of rides. Each line can represent 1. So that'd be 5 rides there. Well, all the way up to 10 rides for us. And the cost, we need to get it to 45, right? So I'm going to see each line is $5. So there's 10, 15, 20, 25, 30, 35, 40, 45, 50. I definitely would not want to show that each of these lines is $1 because you wouldn't get the $45 there, okay? So let's put these points on the graph as many as we can. So for 0 rides, $45. 1 ride, $45. 2 rides, $45. $45 all the way through. Okay, and we see this gives us a straight horizontal line. Again, I'm not connecting these dots because if you said you went on a half a ride, you'd be kind of stuck. You could be stuck upside down. That doesn't seem very healthy. Okay, but then let's say, is this a function? Well, let's look at the table. We don't see any x values repeat. Now they could. Like you could go, like we've shown 5 times. Let's say you went another time and you went on 2 rides. How much would it cost? Still 45. So no matter how you look at this table, right, even if you had repeating values of x's, the y values are the same. So we would say this one is a function, just from the table. And then the graph, again, we'll run a vertical line test here. So here's my vertical line. I scan it. It's only going to touch once no matter where I put this vertical line. So this also would show that it is a function. All right, this table shows the number of hours Owen plays his favorite video game and the number of points he scores. Is the number of points Owen scores a function of the amount of time he spends playing? Why or why not? Okay, so to determine if this is a function, again, we're going to look at the x values. And for a vertical table like this, generally speaking, the x values are on the left and the y values are in the right column. So I say, okay, is there any x values that repeat? And I find 3 times that it repeats for 1, and it repeats twice for 2, like this. So I look at the ones first, at least that's where I'm going to start, and I see that the corresponding y values are different here. Since those y values are different, this is not a function. So that also means that if Owen was playing, he'd have to get the same amount of points if he plays for 1 hour every time, or for 2 hours for that matter. But yeah, even the 2 hours show that they're different y values, so still not a function, okay? It's not a function because the x values that repeat, say matching x values have different y values. Boom. All right, this is a really nerdy way to say what a function is. It's just saying if you got x values, for every x value you have, no matter what the x value is, you can only have one corresponding y value, which we've already shown with the tables and the graphs, okay? So there's our objective. I can determine when a relation is a function, and hopefully we feel pretty good about that by this point.